Today in the workshop we are using soil moisture sensors. We'll learn how these sensors work, how to calibrate them, and how to use them with microcontrollers. We'll also build a soil moisture meter and an automated watering system that you can control with the Arduino IoT Cloud. We're growing something special today, so welcome to the workshop. Well, hello and welcome to the workshop, and today we're working with soil moisture sensors, which you can probably guess from their name are devices that you place into the ground and they'll measure the amount of water content in the soil. Now we're going to learn about how these sensors work, we're going to calibrate a few of them, and then we're going to build a couple of projects. The first project is a soil moisture meter with an OLED display, and our second project is an automated watering system that's going to be using the Arduino IoT Cloud so that we can water and maintain our gardens from pretty well anywhere in the world. Now, before we go on with our lessons and our projects, there is a bit of a disclaimer I have to give. Now, there are some people out there, perhaps you're one of them, who are just wonderful with gardening. They can grow beautiful crops of vegetables, they can make gorgeous flowers, they're just whizzes in the garden, and we call these people people with a green thumb. Well, if you look on the color wheel, the opposite of green is red, and so I probably have a red thumb because plants do not do well with me. I've never been good at gardening. I've even managed to kill plastic plants. So I'm not the kind of person who can dispense advice about gardening to you. I can, however, dispense advice about technology. So let me dispense some right now by telling you how soil moisture sensors work. Soil and moisture sensors have applications in agriculture, irrigation, research, and just plain gardening. Some advanced soil moisture sensors use the property of water to alter microwaves, and they use techniques such as frequency domain reflectometry and time domain reflectometry. A very advanced method of measuring soil moisture is neutron scattering, which uses the moderator properties of water on neutrons between a source and a sensor. The soil itself can also act as a galvanic cell. This allows the construction of a soil moisture detector that does not require its own power source. The resistance and capacitance properties of soil can also be used to measure soil moisture. Today we'll be focusing on inexpensive sensors designed for microcontrollers and microcomputers. These sensors are based on either the resistance or capacitive properties of the soil. These sensors can be run in multiple modes. In analog mode, the resistance or voltage output will change in response to the amount of moisture in the soil. In digital mode, a set point is established and the output will go either high or low depending on whether the moisture is above or below that set point. In addition to analog outputs, there are also serial and I2C devices available, and we'll be taking a look at an I2C device later on. A common application for soil moisture sensors is an automated watering system, and we'll be putting one of these together later on in the video. In this sort of system, a soil moisture sensor is connected to the input of a microcontroller. It's also typical to have some sort of a readout of soil moisture as well. You will also connect the pump or other source of water to the output of the microcontroller. If the sensor detects the moisture dropping below a certain point, it will activate the watering system and water the soil. Once the moisture has gone above a certain threshold, the watering will stop. Resistive soil moisture sensors depend upon the resistance property of soil, which decreases with the amount of moisture in it. These are very simple to design and quite easy to manufacture. However, they have one major drawback in that corrosion of the probes can alter its resistive properties. With a capacitive soil moisture sensor, the soil itself serves as the dielectric within a capacitor. These sensors have a timer on them that measure the amount of time that this capacitor takes to discharge. Because we're measuring soil capacitance, we don't require any direct contact to an electrode, so the electrode can be insulated, and this eliminates the corrosion effect that occurs with resistive sensors. Resistive sensors have an advantage in that they are a lower cost. Capacitive sensors, however, are longer lasting and generally provide better performance. As these sensors both provide analog outputs, they can both be used in our designs, so you can use any sensor you happen to have with the circuits you're about to see. So now let's take a look at a few soil moisture sensors. Now here are some soil moisture sensors for you to take a look at. We're going to be using a few of these later on in some experiments. 3 of these are capacitive sensors and one of them is resistive, and you can sort of tell which one the resistive one is. It's this one here, and it has these 2 electrodes, and what we're actually doing is measuring the resistance between the electrodes. So when that's inserted in soil, the soil will provide an electrical resistance, and that's what's being measured in these. The rest of these are capacitive sensors, so you don't actually see any electrodes. They've all been nicely sealed up and protected from the elements, so there's nothing going to corrode because, of course, a capacitive sensor works on a different principle. In this case, the soil becomes a dielectric in the capacitor. Now, this is a very standard and very common capacitive soil moisture sensor, and these ones are quite inexpensive, and it has an analog output. These other 2 have I2C outputs. This one is made by a company called Catnip Electronics, and it's a very interesting little sensor. It also measures temperature and light. One other thing about it, though, is it didn't have a connector on it, so I had to solder these jumper wires onto the output here, but this has an I2C output, so I've got power, ground, SDA, and SCL coming out of here. This is also another I2C sensor, and this one is called a Seesaw, and it's made by Adafruit. It does have a little connector on it, so it's a little bit easier to use, and these other ones also have connectors as well. But there you go, a few soil moisture sensors that we can be using in our experiments. Now, before we put our soil moisture sensors to use, we need to calibrate them. It doesn't matter whether they're resistive or capacitive. Each sensor has its own unique properties, and even if you get a batch of them, you'll find that no 2 of them are exactly alike. Now, calibrating the sensor is pretty easy. All you need to do is take a measurement of its output when it's completely dry, and then take its output measurement when it's completely wet. And since resistive and capacitive sensors both output a voltage in response to the amount of soil moisture, we can use the same circuit and the same sketch to calibrate both of them. Now, I'm going to be doing this with a Raspberry Pi Pico. It's an inexpensive microcontroller, and one of its advantages is that it has a 12-bit analog to digital converter, so we can get a very accurate reading from it. Now, I'm also going to be using the classic Arduino IDE 1.8 for these experiments, and if you haven't used the Pico yet with the Arduino IDE 1.8, I urge you to go and take a look at that monster-sized video that I just did for the 10th anniversary of the Raspberry Pi. You don't have to watch the whole video, but go to the 3rd project. You can use the table of contents in the video to go there directly, or use the chapters feature on the YouTube video. The 3rd project was a Raspberry Pi Pico Simon game, and I show you exactly how you set up the Arduino IDE to use the Pico. So I'm going to assume you already know how to do that. Now, if you don't want to use a Pico, I'm also going to show you how you can use these calibration with a Arduino Uno, and it's basically the same sketch with one modification, and I'll show you the hookup for the Uno as well. So you don't necessarily have to use a Pico, although you will get more resolution. So let's go and take a look at how we hook up the Pico, and then I'll show you the sketch that we're going to be using to calibrate both our resistive and capacitive soil moisture sensors. For our experiments, we're going to be using a Raspberry Pi Pico microcontroller. However, you could use a different microcontroller, and I'll show you how to do the same experiments with an Arduino Uno a little bit later. We will also, of course, need a soil moisture sensor. You could use a resistive sensor or a capacitive sensor because the hookup and the code are identical for both. I'll be using a capacitive sensor in this illustration, but again, the hookup for the resistive sensor is identical. We'll start by connecting the analog ground pin of the Raspberry Pi Pico to the ground of the soil sensor. You could also use another ground pin if you wish, but analog ground is the specific reference for the analog to digital converter and will produce the best results. We'll use the Pico's 3.3 volt output and connect it to the VCC of the soil moisture sensor. And analog to digital converter 0 input, which is also GP26, will be connected to the output of the soil moisture sensor. And this completes our wiring. Now let's take a look at some code we can use to calibrate our sensor. Now here's the sketch that we're going to be using to calibrate our sensors, and we can use this with both capacitive and resistive sensors, and it's an extremely simple sketch. We start off by defining a value that we're going to be using to get the sensor value, and this will be the output of the analog to digital converter, and then we define the analog to digital converter pin itself, which is ADC0. Then we'll open up our serial monitor so we can see our results. And we're also going to set our analog to digital converter resolution to 12 bits. If we don't do this, it'll default to being 10 bits, and we want to get all the resolution we can. And then in the loop, it's extremely simple. All we do is we use an analog read to read the value from the sensor pin and assign it to sensor val. And then we just print that to the serial monitor. We add a very short delay and we continue to do that. And so a super simple sketch. Let's try it out with both capacitive and resistive sensors. So we're going to start off by calibrating the capacitive sensor, which I've got hooked up to the Pico right now. And as you can see in the serial monitor, I'm getting a reading, and it's hovering around 2500, 2523, 2518. This will be my dry reading, and I want to record that because this is what I'm getting at what should be about 0% moisture. Now I'm going to stick it into this glass of water, and you'll see that the reading went down, and it's going down about 1340, 1350. This will be the reading that I'm going to get for my wet reading, and so you'll also want to calibrate that. So those are the two different extremes for the sensor, and we'll be using those calibration values in further experiments. Okay, now we're working with the resistive sensor, and the first thing you'll notice on the serial monitor is that the dry reading is a very, very low value. It's down around 20. It even approaches 0 at times. And when I put it into the water, you'll notice that the wet reading is very high, and there's quite a discrepancy between the two. And with that kind of a range, it means that this type of soil moisture sensor is actually more sensitive to small differences in soil moisture. So in some ways, it's a bit more accurate. However, of course, the resistive ones do have a problem in which the probes will eventually start to corrode, and the values will start changing. They'll go out of calibration. But as you can see, we can use the same circuit to calibrate both resistive and capacitive soil moisture sensors. Now you could also use an Arduino Uno to perform these experiments. Again, I'm showing a capacitive soil sensor, but you could use a resistive sensor as well, as the hookup is identical. We'll start by hooking the ground of the soil sensor to the Arduino's ground. The VCC of the soil moisture sensor will be connected to the 3.3 volt output of the Arduino Uno. The output of the moisture sensor will be connected to analog pin A0. And you'll also want to connect the AREF or analog reference pin on the Arduino Uno to the 3.3 volt output. Now let me show you the changes you need to make in the code in order to use an Arduino Uno. Now there's only one change you're going to need to make in the code to run this with an Arduino Uno, and it's down here in the setup. This command analog read resolution is not going to compile with an Arduino Uno because the Arduino Uno only has a 10-bit analog to digital converter. At the same time, if you remember in our wiring, we've wired the AREF or analog reference pin to 3.3 volts, so we need to use that. So change analog read resolution to analog reference and make this value here external, like this. And that way you'll use the 3.3 volt power supply that we fed into the AREF pin, and you also won't have an analog read resolution that was set there. So obviously this line is incorrect right now. But that's the only change you need to make, and you can run the code on an Arduino Uno. Now, when I showed you all of the different soil moisture sensors that I've collected, I showed you two models that were using an I2C interface. Now, these are capacitive soil moisture sensors, and so they work in a similar fashion to the capacitive sensor we've already worked with, but of course their output is different. They are I2C, and therefore they can be used with just about any microcontroller or a microcomputer that supports I2C. Now, one of the models I showed you was from a company called Catnip Electronics, and it's a very interesting sensor. Not only does it give you soil moisture readings, it also outputs temperature and light level readings, and it's quite easy to use as long as you use a library with it. So we're going to take an Arduino Uno and my Catnip Electronics I2C sensor and see how we put them to use. For our I2C experiment, we'll be using an Arduino Uno. We'll also require a Catnip Electronics I2C Moisture Sensor, and you'll need to solder some wire onto the connections in order to make use of it. We'll begin by connecting the ground connection on the moisture sensor to one of the grounds on the Arduino. We'll connect the moisture sensor's SDA output to analog pin A4 on the Arduino. We'll connect the SCL input to analog pin A5. And the VCC pin on the Catnip Electronics I2C Moisture Sensor will be connected to the Arduino's 5-volt output. And this completes our wiring. Now let's take a look at some code we can use with the moisture sensor. Now the I2C soil moisture sensor that we're going to be using is a great example of some of the electronics that we're seeing from all over the world. This was built by a company called Catnip Electronics, and they're in Lithuania. Now you can get this off of Tindy where they sell it directly, and as you can see it's not particularly expensive, but I actually got mine from Mouser Electronics, and so you have that as an option as well. Now wherever you happen to get it from, you're going to need a library in order to use it properly. And there are a lot of great examples up on GitHub for doing that. There are also Python examples up on GitHub, so you could use it with Python or MicroPython, use it with a different microcontroller, or perhaps with a Raspberry Pi. But we're going to be using it with an Arduino Uno, so we're going to get some Arduino code, and here's where you can grab a library on GitHub. You just hit code and do download zip, and you'll get the library in a zip format. Now you'll need to install that into your Arduino IDE, which I've just done, but I'll show you how you do it. You just go under Sketch, you go Include Library, and then from Include Library you do Add Zip Library. You navigate to where you're downloaded your files, and here it is, the I2C soil moisture sensor. You would hit OK, but I've already done that. And now you've installed the library, there's also an example sketch that we can use in order to work with it. So just go into File, go into Examples, go down to Examples from Custom Libraries, and you'll see I2C Soil Moisture Sensor. And you've got two of them, one that allows you to change the I2C address on the device, the other one called Read Sensor Data, which is what we're going to do. And so I'll just expand that so we can see it. And it's a pretty simple sketch, really. It includes the library that we just installed, and also includes the wire library, of course, because we'll need that for I2C. And it defines something called sensor. And we go into the setup, we'll start the wire library, we'll put our serial monitor on, and we'll reset the sensor with a sensor.begin. We'll give it some time to boot up for a second, and then we'll print out to the serial monitor the address of the soil moisture sensor and its firmware version. So we'll use a get address and a get firmware, get version, excuse me, to show the firmware version of it. And then we just go into the loop, and we wait if the sensor's busy, and then after that we'll print out the capacitance value. So we use get capacitance to read that and print it out to the serial monitor. This also reads temperature and light, so we'll get the temperature and we'll get the light, and these are just simple commands that are made possible because of the library, and these are just printed out to the serial monitor. So you could see how you would use these in your own sketches. So this is a really cool little sensor, and with this library it should be pretty easy to use it. So let's just load up the code and take a look at it in action. And so we're going to do a quick demo of the I2C Moisture Sensor. And if you look at the serial monitor, you can see that we're getting capacitance, temperature, and light readings as well, too. And so those could also, I suppose, be useful for your gardening needs. Now, this is the dry reading that we're going to get. Now, remember, this takes about a second or so before it gets the reading, so it's not going to be instantaneous. I'm going to put it in here. And there you can see now that the capacitance reading has changed. The temperature and light readings have changed quite a bit as well too. And so I'm not sure how you interpret the light values. The temperature is in degrees Celsius, and I think it's a little bit off because I don't think the water is really that warm. And the capacitance is really, of course, what we're looking for. This is the capacitance when it's wet, and I'll remove it again and dry it off. And we'll wait a second or so, and it drops down around 187, 185. So once again, this is a useful soil moisture sensor, and because it's an I2C device, you can use this with microcontrollers and microcomputers that don't happen to have an analog input. So now that we've seen how soil moisture sensors work and we've calibrated a few of our own sensors, it's time to put them to use. And the first project we're going to build is a soil moisture meter. Now this meter has an OLED display that will display the percentage of moisture in the soil. It is based around the Raspberry Pi Pico. Now you're going to need the calibration values you took for your soil moisture sensor in order to complete this job. So if you haven't done that yet, go back and calibrate your sensor first. And after you've done that, let me show you how you wire up the soil moisture meter. We'll be constructing our soil moisture meter with a Raspberry Pi Pico. We'll also be using an OLED display, a standard SSD 1306 display with an I2C input. And of course we'll require a soil moisture sensor. Again, you could use a resistive or a capacitive sensor, and I'm illustrating a capacitive sensor here. The connection for the soil moisture sensor is identical to the ones we used for calibration. We'll start off by connecting the ground of the soil moisture sensor to the analog ground or AGND pin on the Raspberry Pi Pico. The VCC connection on the moisture sensor will go to the Pico's 3.3 volt output. And the output of the soil moisture sensor will go to analog to digital converter 0 input on the Raspberry Pi Pico. This is also GP26. We'll connect the ground of our OLED display to any of the grounds on the Raspberry Pi Pico. You can identify the ground pins on the Pico as they have square pads. We'll connect the VCC of the OLED display to the 3.3 volt output of the Raspberry Pi Pico. The SCL or clock pin on the OLED display will be connected to Pico pin GP5. And the SDA or data pin on the OLED display will be connected to Pico pin GP4. And this completes our wiring. Now here's a sketch that we're going to be using for our soil moisture meter, and it's been written to use capacitive sensors. However, you could rewrite it for resistive sensors with one simple change, which I'll show you in a moment. Now we start off by including some libraries that we're going to need to drive our OLED display. We need the wire library because that's the library for I2C, and that's already included in your Arduino IDE. The next couple of libraries are libraries from Adafruit, and if you don't have them, go into your library manager and look for SSD 1306. Install the Adafruit library, and it'll also install this other library for you. However, if you've already played with OLED displays, there's a good chance you have these libraries already. Now we're going to go and set some parameters for the OLED display. So we set its height and its width, and we set some other parameters up as well. This reset as -1 just needs to be set so we know that we're not using a separate line for reset. And the screen address, and this is the I2C address. Now, if you happen to have a display that has been set to a different I2C address, you will of course need to change that. Then we define an object called display by passing it all of the different parameters for the OLED. And then we go and we put in our sensor constants. Now these are the values that we determined from the calibration sketch that we ran earlier. So your values could very well be different than mine. You could start off with these and experiment with them, but the best way to do it is just to calibrate your sensor using the sketch that we looked at previously, and then plug the values in over here. We set up a couple of variables we're going to need for the soil moisture. We're going to get the soil moisture value, which is actually the value that we get from the analog to digital converter output, and we're also going to get the value in percentage, which is what we want to display in our display. And then we define the port that we're using, which again is ADC0 for the input from the sensor. In our setup, we're going to set up the serial monitor, and we're just using the serial monitor for troubleshooting, and also so we can fine-tune those wet values and dry values up over here. We might want to change them, and the serial monitor will help us do that. We're going to initialize our display, and an important thing when we initialize it is this switch cap VCC parameter that we use when we initialize it. If we don't use it, if we just use SSD 1306, it's going to expect the 5-volt power supply, but in this case it'll know it's getting a 3.3-volt power supply, so you need to plug that in, and then the screen address itself. Then we're going to clear our display, and once again we'll set the analog to digital converter to use 12 bits with an analog read resolution function. Then we go into the loop, and in the loop, just as we did with the calibration sketch, we're going to get the value from the sensor, assign that to the soil moisture value, and we'll print it out to the serial monitor. And then we'll go and we're going to determine the percentage, and we do that with a map command. And we take the soil moisture value and we map it between the dry value and the wet value to a value of 0 to 100 to get the percentage. Now, I said earlier that you would possibly be able to use this with a resistive sensor, and you can. What you need to do is just reverse the order of dry value and wet value, because as we saw, the values work in the opposite direction for resistive sensors. Now, it's possible these values could drop below 0 or above 100 if we get values that go beyond the dry value or the wet value, and that can happen if the calibration isn't perfect. And so we're going to use a constrain command to constrain our results between 0 and 100. So if it goes over 100, it'll just read 100, and if it goes below 0, it'll just read 0. And you can use the serial monitor to fine-tune things so this doesn't occur very often. And we print that out to the serial monitor, the percentage we've had, and then we just go and print to the OLED display. So we set the cursor on the OLED, we set the text size to 2, and the text color to white. Now, the top of my display is yellow, but it doesn't matter. You use white all the time as the color when you're writing to an OLED display. And then we print the word moisture, and that's going to print on the top of the display. In the case of my display, it's going to be yellow, but your display may be just one single color, or it might be 2 different colors. It doesn't matter. And then we go and we move our cursor down again, set our text size even bigger, and again setting the color to white. Then we'll print that soil moisture percentage value. We'll print the percent symbol behind it. And then at the very end of that, we will do a display, which actually puts everything onto the OLED, because nothing is written until we do that. We're just basically filling a buffer over here. We'll delay for a quarter of a second, and then we'll clear the display so we can go back and get the next reading. And that's basically the entire sketch. Just load it up to your Pico and take a look at the results. And so here we have our soil moisture sensor on this small solderless breadboard, and I've got a couple of things to test it with over here. Now it's reading 0% because the sensor is just loose in the air. Let's just drop it into the water here. And as you can see, it goes up to 100% right now. Now, by the way, you might be seeing some flickering on this display. The flickering is just because of the cameras. It's an effect that they are making. It probably has something to do with the frame rate or something, because there is no actual flickering that you can visibly see. I just wanted to point that out. Let's put it into some soil right now. Just move these wires a bit so we can see it. And this isn't particularly moist soil. Let's see if I can find a moist spot on it. Oh, there's a moisture area. There we go. I had dropped some water into it and went to one side. So it is indeed measuring the moisture in the soil. And so this is actually a cool little project, and you could build it into its own little enclosure and give it a power supply if you wanted to, and actually make some sort of a useful instrument out of it. Now at the beginning of this video, I illustrated a pretty classic use for a soil moisture sensor and a microcontroller. Essentially, you had the soil moisture sensor attached to the microcontroller, and the microcontroller was also attached to a pump or another method of dispensing water. When the microcontroller had detected that the soil moisture had dropped below a certain threshold, it would activate the pump, which in turn would add moisture to the soil, and when the moisture went above that threshold, then it would turn off the pump. And I'm sure you've seen about a dozen different systems for doing exactly that. Well, we're going to build something like that right now, but it's got a bit of a difference. My design is based around an Arduino Nano 33 IoT board, and it also makes use of the power of the Arduino IoT Cloud. And with this, we can make a cloud-based system that we can monitor using our phones or tablets or our computer pretty well from anywhere in the world. Now, I'm going to make the assumption that you already know how to use the Arduino IoT Cloud, but if you don't, I've already done a video on that, and so there's a video and article that you can check out that'll bring you up to speed right away, so you'll understand some of the terminology that I'm using. Before I show you how we wire this up, let me show you some of the features of our cloud-based watering system. Now here's my automated watering system assembled on a solderless breadboard. As you can see, it's got an OLED display that cycles through a number of different values, a temperature and humidity sensor, a relay to drive the pump, and of course the Arduino Nano 33 IoT. Now if we take a look on the control panel for this, you can see that I'm displaying the moisture. I'm also displaying the moisture over a period of time, and this is the live view, but I can go back an hour, a day, a week, or even 15 days. So you can see how the moisture has changed in your soil over a period of time. I've got a live temperature and humidity display, and I'm also displaying the status of the pump, and right now it's green to indicate that my pump is on, and that's because I've got the trigger level set to 40, but I can adjust the trigger level over here. So let's bring it down to 20, which is below the 30% moisture. So we have to give this a few seconds for it to react. And there you go. The pump status is now changed to red, indicating that the pump is off. And so now let me show you how you can wire up this project. To build our IoT watering system, we'll be using an Arduino Nano 33 IoT board. You could probably also use an Arduino Nano RP2040 Connect board, and they're pin-for-pin compatible. We'll be using a capacitive moisture sensor, and the DHT22 temperature and humidity sensor. Now you may wish to use a DHT21 as it's more suitable for outdoor applications. You could also use a DHT11 if you wish, and I'll show you where you can make some changes in the code to use one of those other sensors. We're going to be using the same OLED display that we used when we constructed our moisture meter, and we'll be using a 5-volt relay module. Now you'll also need a pump, and you'll need a power supply to drive that pump. I would strongly suggest using a low voltage DC pump. We'll begin by connecting pin 1 of the DHT22 to the Nano's 3.3 volt output pin. We'll connect pin 2 of the DHT22 to Nano pin D8. And pin 4 of our DHT22 will be connected to one of the Nano's ground pins. The moisture sensor's output pin will be connected to the Nano's pin A0. The moisture sensor's VCC will be connected to the Nano's 3.3 volt output. And the ground from the moisture sensor will be connected to one of the Nano's grounds. The OLED's ground will also be connected to one of the Nano's grounds. The OLED VCC will go to the Nano 3.3 volt output. The SCL connection from the OLED will be connected to the Nano's SCL pin, which is also address pin A5, but note that on the Nano it's not usable as an analog pin because it has an internal pull-up resistor. The same goes for the OLED's SDA pin, which is connected to the Nano's SDA pin, which is also A4. The relay module's G or ground pin is connected to the Nano ground. The relay module's 5V pin is connected to the Nano's 5-volt output. And the module's input pin is connected to Nano pin D3. You'll also want to run the power supply for your pump to the common output on the relay. The relay's normally open output will be connected to one side of the pump, and the other side of the pump will be connected to the pump's power supply. And this completes our wiring. Now let's go into the Arduino IoT Cloud and see how we can build this project. Now we begin our project up on the Arduino IoT Cloud, and as I said earlier, if you're not familiar with the IoT Cloud, I strongly suggest you check out the video and article that I did about using the IoT Cloud to get yourself up to speed. But essentially, when you're building for the Arduino IoT Cloud, the main thing that you're building is called a thing. It's, after all, the Internet of Things. And this is the thing that I am building, and I've called it Auto Water. And a thing has three different components to it. It has variables, it has a device, and it has a network. Now my device is the Arduino Nano 33 IoT board that I've already registered with Arduino, and my network is of course my own Wi-Fi network, and so I've got the credentials for my network over here. And then we have our variables, and these are the variables that we have for my project, and there are actually 5 variables for it: the current moisture, the current temperature, the current humidity, the pump status, the status of the pump, whether it's on or off, and a trigger level, which is the level that we are going to tell it to trigger and turn the pump on. So this is the percentage of moisture level. Now I'll show you some of the variables. If you go into current moisture, for example, you'll see that it's an integer, and I've set it to read only. And if we go into the current temperature, we'll see that it is a float, and it is also set to read only, and it sends the values on change. And that's actually one thing about current moisture, if I go back to it, that I have set. I set it to go on change, and that means anytime the moisture value changes, it'll send something up to the cloud and it'll update my dashboard. Now, since I'm using that graph on the dashboard, if I keep it, let's say, at 0% or 100% for a long time, the graph won't change. So you could actually go into the variable if you wanted to, and you could edit that, and instead of doing on change, you could say periodically and give it a time period, and that might be a good thing to do if you wanted the graph to be more constant. So that's just something you may want to change in yours. Current humidity is the same as the temperature. It's a floating variable. It's read only. The pump status is also read only, and it's a Boolean. And the trigger level is a bit different. It's an integer, but it's got read and write permissions, and that's because I'm using a control on the dashboard in order to set the trigger level. So I have to be able to both read and write that value. Now, if we go back onto my dashboard, you'll see all the various components that I have, the moisture, and right now the sensor is completely out of the water, so it's dry. It's down at 20%. And here's the graph of everything, and you notice the graph actually hasn't updated itself for a little while because it's been down at 20% for a long time. And as I said, if you made that work periodically, you would see the graph update a lot. If I end up putting the probe into the water and changing that moisture, all of a sudden the graph should come back to life. And as I said earlier, there's a bit of a latency over here, so it's actually already happened. The pump has turned itself off, but we don't see it here right away. And there it goes. We see it right now, and you see that whole period of time where I didn't get a reading because it was constantly at 0, and now it'll stay at 100 until I take it out of the water. So again, you may want to change that to trigger periodically instead of on change. Let me show you how these are done on the dashboard. So I'll go into edit mode. We go to moisture, and we can go and edit the settings. And in moisture, I've got it linked to the current moisture from Auto Water. So if I wanted to do that initially, what I would do is I would go in here and get a list of my things. I'd pick Auto Water, and it would give me all of the potential ones that it would link to. And notice, for example, pump status has been grayed out, and that's because that is a Boolean, and it won't work for this kind of thing. So it will just look at the variables that are applicable, and in this particular case, it was current moisture. I'm actually not going to change anything, so I'm going to set it to done. In order to use the graph is very simple. It's exactly the same, actually. You just set it to link to current moisture. There's really nothing else you have to do to the graph because all of the heavy lifting, so to speak, has been done by the IoT Cloud to make that neat display. Temperature and humidity, as you can imagine, are linked to their associated variables. The pump status is linked to the pump status, which is the Boolean, and I've got it set so that it's an LED, they call this one over here, is the type of a control I used over here. And you can change this to use only one LED or the two, so I decided to use the two LEDs. And so I have a green one and a red one. And then the trigger level over here is linked to the trigger level variable. And of course, this is a two-way variable. It's read-write. So as I change this slider control, it will change the value of trigger level, and I can pick that up in my code. So now let's go and take a look at the code. Now, when you go into the IoT Cloud, it actually builds code for you. It does a sketch over here, and you can go and open that in the full online editor. What I did is I built this. I went into the full online editor and added my libraries, but then I did the rest on the Arduino IDE 2.0 because you can link that to the cloud as well too. And I find it a lot easier to work on this because you've got all sorts of different features here that you don't have on the online editor. So this is a sketch in the Arduino IDE 2.0, but of course you could build it on the cloud as well too, and it'll work just fine. It starts off by including Arduino secrets, and the Arduino secrets is a file that's included here. I won't show you my Arduino secrets file because that's what contains the SSID and the password for my network. And but that comes along in the package with the files. There's also another one called thing properties that comes along with it as well. Now it tells you that these variables have been automatically declared, so you don't need to declare them in your code. And these are the ones that I declared up on the cloud. So you'll notice my 5 variables over here. Now these libraries, again, I installed through the cloud, which is why there are so many library files, but basically it's the same ones that I installed for the moisture sensor, the SSD1306 and the GFX libraries from Adafruit. It just added a few other ones. I just took them there because that's what the cloud installed. I also installed the DHT sensor library for my DHT22. And by the way, you could also have used a DHT21 or DHT11. You'd install the same library. And I installed the wire library for I2C. And then after that, we have some stuff you've seen before in the sketch that we did for the moisture meter that set the OLED size, the OLED parameters, and set up the OLED. It's basically the same thing. This is just the parameters for the DHT22. So if you decided to use, let's say, a DHT21, you would just change this here to DHT21 or a DHT11, etc. Otherwise, the code is the same. And our DHT pin is pin 8 because we're using data input 8 for the sensor. Now I've defined some local variables for the temperature and humidity, and you might find that strange because of course up over here there are cloud variables for it, but the reason I'm doing local variables for that is because when you first start this up, you're not actually connected to the cloud, and so I'm not quite sure exactly what is going to happen. So I want local variables so that this can work even when it doesn't have an internet connection. I don't want it to be completely dependent on the cloud for the local thing to work, because after all, it's controlling a pump with water. I want it to be in a controlled situation. Now, these constants you've seen before, the dry and the wet value for our probe, for our moisture sensor, and of course we need to determine those experimentally, and so your values could quite well be different than mine. And then this, again, we've seen it's identical to what we did for our soil and moisture meter. We get the moisture value, which is the value coming from the A to D converter, and the moisture percent, which is our converted version. And then the sensor input is on analog pin A0. We've got that. The relay port is defined on pin 3. And then the pump status text, this is just what's going to print on the pump status, either on or off. I've defined a variable for that, a string variable, and I've given an initialization value of off. And I've also given it a trigger value. And again, of course, I've got a trigger that's up on the IoT Cloud, but I want a local trigger. And so I set it to about 30 because I thought that was a reasonable trigger point for the water. You could change that value if you like, but basically when it starts up, before it can connect to the cloud and see where the trigger has been set, it's going to use a value of 30. And then this has been inserted for me with the Arduino IoT Cloud. It's one of the many things it inserts, and it includes another file called thing properties, and that's this file over here. And thing properties has been generated in the cloud and includes all the different variables that I'm using. So it defines them over here. And init properties over here just initialize all the different properties. It tells you what it is: current temperatures, read, on, chain, and a default value of null, etc. And so we go now into our setup. And setup, this again was added by the IoT Cloud. This sets up the serial monitor, and you notice it gives it a rather long delay of about 1.5 seconds afterwards. And so again, this is going to take a couple of seconds for everything to establish itself, and this is part of that delay. We just saw init properties, that's in the thing properties file, and it connects to the Arduino IoT Cloud. This again has been added automatically when I generated the initial sketch in the cloud, and so is this, and this is just a debug level thing, and you can change the debug level if you wish to. You can set it all the way up to 4 if you want to get all kinds of information if you're having problems. We saw this before to initialize our OLED display using the 3.3 volts, so that's over here. We initialize the DHT22, and this will work also with the DHT21 or 11, so we just do a begin, set our analog to digital converter to use 12 bits as we've seen before, set the relay as an output, and we'll turn off the relay initially because we want this to start always with the pump off. Even if the soil is bone dry, we'll wait a second or so to establish that. We don't want to start by running the pump, and we set the pump status, which is the cloud variable, to false because again we've set the pump off. And then we go into our loop. Now the first thing in the loop is something the cloud added by itself, and that's an Arduino Cloud update function to just update between the cloud and the local machine here, the Arduino Nano 33 IoT. Then we're going to get our temperature and humidity from the DHT, and we'll assign them to the local variables, and then we'll pass those values off into the cloud variables. And so we've got both a local and cloud variable with the same value. We're going to go get the moisture value and determine the percentage and keep the values between 0 and 100 exactly the same way we did in our soil moisture meter. And then we print that out to the serial port. We can just use that if we need to calibrate our soil moisture sensors. And then we'll pass that to its equivalent cloud value, the current moisture value, which is a cloud variable, gets the same value as this. Now we go and see if our pump needs to be triggered. And so basically if the soil moisture percent is a lower value than the pump trigger, then we're going to turn the pump on, and otherwise we're going to turn the pump off. And so pump on and pump off are two functions I'll show you in a moment. And then we go to cycle the values on the OLED display, and I've got a couple of functions here called print OLED, and we just pass a number of parameters to them, and you can actually even see the parameters thanks to the Arduino IoT Cloud. And basically we're pumping the position and the value of the top text, the position and the value of the bottom text, and then the delay period, how long do we want it to be on. And so let's go and take a look at those functions because that's the end of our loop. Pump on and pump off are pretty simple. For pump on, we do a digital write to the relay and we write it high to turn it on. We change our status text to on, and we change pump status, which is the cloud variable, to true. Pump off does exactly the opposite thing. Print OLED, as you've seen, all the different parameters you put on its input is basically the same as what we saw when we built the soil moisture meter. Instead of using fixed values, we're just using the variables that we pump in. So we set the top cursor text size to 2, and we set its position to whatever this value is on the first line, line 0, and we print the top text. And then we set the main cursor on line 40 to whatever position main cursor is, set the text size to 3, and then we print the main text. And then at the very end of it, we do a display. We delay by that delay time and then clear the display. And so this just saves me from having to write this 4 times over. And then finally, on trigger level change, this is something the cloud added because every time that I change that trigger variable, this function will be activated. So when I move the slider, it will activate this function, and all the function is doing is it's taking the trigger level variable and it's setting the local pump trigger value to that trigger level variable, and that's basically it. So that's the sketch. It may look a little overwhelming at first, but actually when you break it down, it's quite simple. And once you set that up with the cloud and your control panel, you're all set to go. Now, in order to demo this, I found that it was a little bit awkward in the workshop to actually use soil and a pump, and so I've used a different method, but I wanted to show you the kind of pump that you could use with a system like this. Now, this is a tiny pump that would be perfect for this. The pump is actually submersible, and it runs on 4.5 to 12 volts DC, and it actually pumps a surprising amount of water, which is one of the reasons I refrained from doing this on my workbench, because I didn't want a surprising amount of water all over my workbench. But this is a fairly inexpensive unit that is typical for the kind of thing that would work perfectly in this application. Now, instead, what I have done is I've just wired my relay over to this lamp over here, and so the lamp will come on in lieu of the pump. And instead of soil, I've just got a cup of water, and of course, if I immerse this into the cup of water, then it's going to go to 100% moisture. And at 100% moisture, that's obviously not going to trigger my pump. And we can take a look at the display. Yes, it's at 100% right now, and so is the display up on the control panel. Now I'll take this out, and if I wipe it completely dry, of course I'm down to 0% moisture, and my light has come on right now to indicate that the pump would normally be coming on, and it says pump on over here on my display. And on the display over here, it's also dropped down to 0% on the control panel, and you can see that my pump is on. But what I can do to simulate levels in between 0 and 100 is I can dip it in the water and then just take it out and leave a little bit of water sitting on the probe. And what that tends to do is it tends to make the moisture somewhere in between. Like right now it's saying it's at 16%, and so that allows me to simulate everything without again having to use actual soil. Now, you've already seen the control panel and you've seen how it works, and it seems to work pretty well. Now, one thing I've noticed is there is a latency between when things happen. Like, for example, right now the pump just turned itself off because the moisture's actually gone up to 21%, but it took a moment for the display to register that, and that seems to be pretty typical. I think it's the time that it takes for everything to travel through the internet and then to go over and register at Arduino's cloud and then to come back to the microcontroller. Also, when you first turn this on, there's almost a delay of about 2 minutes before it starts to collect data, which is one of the reasons that I put those constants in for things like the pump trigger level, because I didn't want it sitting there without any values when it first powered up. But otherwise, it's actually a pretty effective system. I've been running it for a few days and it seems to work pretty well. And I think this is something that either by itself or a variation of this would work well for watering your own garden automatically using the Internet of Things. So that brings us to the end of the video. I hope that you enjoyed it, and I want to assure you that no plants were harmed during the making of this video. Now, if you're at all curious about my ability to kill plastic plants, all I can say in my defense is that they really should print warnings on those things to say that they aren't dishwasher safe. But my horticultural inabilities aside, if you'd like to learn more about soil moisture sensors or get the code that you'll need in order to build the projects I showed you today, you will find all of that on the article accompanying this video on the dronebotworkshop.com website. And there's a link to that article right below the video. While you're on the website, please consider signing up for my newsletter. It's not a spam letter, and it's certainly not a gardening advice letter. It's just my way of keeping in touch with you to let you know what is happening here in the workshop. And it's free to join. All I need is your email address. If you want to discuss soil moisture sensors more, or if you want to brag about your own gardening abilities, head on over to the DroneBot Workshop forums, where you'll find a bunch of like-minded individuals who love to discuss technology and all sorts of things, and the forum, of course, is free to join. And of course, if you haven't yet, please subscribe to the YouTube channel. I make videos about technology and microcontrollers and things that don't have to do with gardening, and all you need to do is click on the red subscribe button, and when you do that, also hit the bell notification, and as long as you've enabled your notifications on YouTube, you'll get notified every time I make a new video. So until next time, please stay safe, please take good care of yourself, and I'll see you again very soon here in the DroneBot Workshop. Goodbye for now.